Yeah, hi everyone. I'm actually Andreas. I'm one of the first author. The chair has now arrived. Oh, sorry.
Good morning, everyone. Can you hear me? Can someone hear me or not?
Works.
Okay, yes, I'm not the chair, but I've been told that you guys don't have any chair. Is it correct? Am I in the right room?
Yes, exactly. I just wanted to start.
Okay, great. Yeah, so I'm supposed to replace the chair. Not that I know what I'm doing because it's my very first session at IXI, but let's try to get that session organized. So as you probably know already, each session each talk is going to be 5 minutes long, and I'm supposed to make sure it doesn't go longer than 5 minutes. Oh, someone says, could you hear me or not? Someone say I can't hear sound clearly. Okay, you can.
No, for me, it's absolutely clear.
Oh, okay. So thank you for that. Yes. So what we might want to do is to make sure that we all ask questions for the authors. Sorry, I didn't have the time to read the papers because I didn't know I would be here today. So let's try to make the session interactive and have you guys ask questions for the authors. And so by prefixing in the chat session under questions, I think, your question by the name of the author. And you guys, please don't respond to those questions in the chat just yet, but let's try to use those questions for the interactive session. So let's start with the first paper in the order. I think it's the order of the official order is the order of the website, I think. But whoever is ready, maybe let's just go with that paper and let's get started. Andreas, I think you were ready, right?
Yeah, thanks a lot. Yeah, okay. In the next 5 minutes, I want to explain to you why you can't trust your vulnerability scanner to detect all known CVEs in your open source packages. So, hi, I'm Andreas, and this is joint work with Henrik and Serena from SAP, Eric from Paderborn University, and Ben from University of Dortmund. The recent Log4Shell vulnerability has once more shown that the use of vulnerable open source packages is a known and dangerous issue. Suddenly, developer needed to detect the vulnerable log4j jar file in all kinds of forms, in Docker containers, on virtual machines, in different server environments, in different jar files, on Nexus servers, or in fed jar files, and also packaged in Lambda functions. Thus, we ask ourselves, in what forms do developers actually and usually include open source packages in their software projects? And how do state-of-the-art vulnerability scanners perform in detecting known CVEs in these different forms? And to give an answer to this question, we first conducted a case study on more than 7,000 projects developed at SAP using the dependency scanners Eclipse Steady, Dependency Check, and the commercial. Generated the software bill of material for all projects and then manually investigating how developers included open source packages. To check the performance of these scanners, we computed the F1 measure of several free and commercial open vulnerability source scanners on these different kinds of forms. So what did we found in our case study? We found that developers include open source package in 5 forms. First, they usually include the jar files directly and unmodified from Maven Central. We also found that a lot of developers actually fork open source projects, do some slight modifications, and then create their own version and indicate it by changing the original open source artifact name slightly. What we also commonly saw were so-called fed jars, so developers bundled multiple open source packages into a single jar file, which contained the names of the original artifacts. A special case that we found were so-called bar fat jars. In these artifacts, like fat jars, they contained all different packages, but the original names of the open source artifacts were lost. And a further special case we found were so-called repackaged jars. In this case, the fully qualified names of the class files were changed to avoid name clashes. So we then computed the F1 measure of open source and free tools on a set of open source packages with respect to this modification and forms, and compared their performance. And what we see that even for unmodified files, the tools yield results, but their performance heavily varies. For the case of patched and fat jars, so where the original artifact names were reconstructible, we saw that all tools still yield results, or most tools still yield results, but their performance decreases. And most interestingly, we saw for bar and repackaged fat jar files that most tools do not yield any results or have a really worse performance. So if the name of the artifact changed or the class file name changed, then the tools did not detect CVEs in these jar files. So it seems, or it's an indication that the tools actually rely on artifact names and class names, but do not actually check the code that is contained in the jar file to detect known vulnerabilities. So to come to a conclusion why we cannot trust vulnerability scanners, our study showed that all tools fail to cope with all different forms that are commonly used by developers. And we saw that these tools, or most tools, do not actually look in the code, but rely on names to identify vulnerabilities. And if the name changes, their performance heavily decreases. And finally, our study showed that if a vulnerability is reported for one particular package, this package usually occurs in many other different projects as well in different forms. So one vulnerability does not usually affect one package, but also a set of other projects that have been released, for instance, on Maven Central as well.
Okay.
So,
thank you so much, Andreas. Perfect timing. So I want to remind everyone to use the chat if you have any question for Andreas. We're not going to answer those. He's not going to answer those questions now. We'll keep the answer for the very end after all the talks. So we are ready to move to the next speaker now. Who is ready to go? The second talk on the website is identifying challenges for OSS vulnerability scanners, but that's the talk that we already had, right? So it looks like, oh, are you guys, did you guys decided to go in the order of MySpace meets? Anyway, who is ready to go? It doesn't matter.
I can go ahead.
Okay, very good. Thank you so much.
Thank you. 1 second. Let me see if you can see my screen.
Yes, we can.
Okay.
Yes,
now
perfect.
I can't see you, so I can only use my screen. So if there's something, please use your mic. There's some kind of noise. I'm not sure. Hello, can you hear me now?
Yes, we can hear you.
Okay, so I'll start now, and you can see my presentation slides, right?
Correct.
Yes. Okay. So I'm Iram Rauf, and I'm postdoctoral researcher here at the Open University in UK, and I'm here to present you our paper that has been accepted as journal first. And the paper is co-authored with my research team that comprises of software engineers, security specialists, and cognitive and social psychologists. And in this 5-minute talk, I will briefly introduce you to our paper, that is titled The Case for Adaptive Security Interventions. Okay, yes, the main message of our of this paper is to encourage software security researchers and software engineers to think of security interventions as socio-technical systems that need to be designed with sensitivity to developers' cognitive load and social contexts. In the context of this paper, we refer to security interventions as those events and actions that occur during the code development process in order to promote developers' security behavior. We suggest and operationalize adaptive security interventions that are responsive to developers' needs. In order to understand influence of developers' socio-technical context on their security behavior and to know what impedes them to meet their security goals, our first research question asks, how can cognitive and social psychology explain the impediments to developers' efforts to meet security goals? Our high-level psychological analysis reported in this paper suggests knowledge, attention, and intention as important determinants to achieving behavioral goal in individuals. We did literature review of developer-centered security literature, and we identified that these three psychological elements also impede developers to write secure code. For example, a knowledge deficit is present when developers use outdated knowledge. Developers' have attention deficit when he loses focus on security when working on functional aspects of the code, and intention deficit occurs when developers considers handling security issues as somebody else's responsibility, or there's a lack of priority for security among the stakeholders. Our second research question investigates how can we design interventions to help developers reduce the obstacles in operationalizing security goals. With the understanding that not all types of interventions can suit every need, we suggest adaptive security interventions. We operationalize adaptivity using MAPE-K loop through the activities of monitoring, analysis, planning, and execution over a knowledge base to vary the response of a system following changes in its operational environment. We make this operationalization concrete with an example and a tool for demonstration purposes, which are detailed in the paper. We present the case that adaptive security intervention should address the security need of developers by monitoring their coding behavior and delivering appropriate security intervention for their needs. The aim of our adaptation is to diversify the channels by which security interventions are delivered. That is not just via IDEs, but also via other communication and collaboration tools. These interventions are delayed. That is, the timings of the interventions are varied and not just instantly inside IDEs. Psychologists suggest that delaying the interventions can trigger long-term behavior change by encouraging users' information recall and avoid the negative effects of frequent interruptions. We also escalate the interventions when some are not effective by not just directing to the developer, but also involving the wider social context, such as the development team and other stakeholders, making it a collective responsibility. And moreover, our interventions are non-transactional. That is, they are a learning process in itself that accumulates knowledge after each iteration and thus can improve that can improve over time. So our research opens many research challenges, and we invite software engineering and security community to investigate such high-level interventions. To conclude, this work highlights the need for new thinking to support a continuum of developers. The case for adaptive security intervention that we presented in this work outlines such a possibility. I thank you for time and look forward to hearing your feedback during discussion.
Great, thank you so much. Perfect timing again. You guys are great. Yes, clap, clap, clap. Great. So let's maybe move on to the next talk on the list, which is the extent of orphan vulnerability from code reuse in open source software. So do we have a speaker for this paper?
Yes, I'm here.
Great.
Hello, I'm
Go ahead,
David
David.
Reed. I'll be presenting the paper, The Extent of Orphan Vulnerabilities from Code Reuse in Open Source Software. Our work is motivated by the security vulnerabilities and other bugs that are propagated through code reuse. Now, we specifically looked at cases where a security vulnerability is introduced into a project, it is copied and committed into other projects, it is then reported and fixed in the original project, but the fix is not propagated to the projects that copied it, often because there's no link from the child project back to the parent. We coined this term orphan vulnerability to describe that specific case. In some cases, the copying is the result of forking, and the link to the original code is readily available. But in other cases, especially when copying is the result of many iterations, the link to the original code may not exist. Either way, the vulnerability is publicly exposed until the orphan vulnerability is fixed or the vulnerable code is removed. And we wanted to study the extent of the problem, its impact, and how to mitigate the risk. And we wanted to study that over as complete a collection of open source software as available. Our aim is to create an efficient way to detect this kind of vulnerability caused by code reuse. We leverage the world of code infrastructure to build a tool to identify code reuse over a nearly complete collection of open source software. And I don't have time to explain World of Code in detail, but basically it contains nearly all open source software in a format that makes research on this scale possible. Now, using our tool, we conducted a case study of several known security vulnerabilities in popular projects. The result is that we found many cases, thousands, even tens of thousands of cases, where the vulnerabilities have been found and fixed, but still persist in projects that use copies of the code. Some of these are inactive projects or forks, but many are active and even highly popular projects. We provided patches to some of those projects and found that only a small percentage of maintainers accepted and supplied our patches. Our contribution is that we provide a working approach to find file-level exact code reuse in any language across open source repositories. We provide a tool to implement our approach, and we conduct a case study with 4 cases to answer our research questions regarding vulnerabilities that are spread through file-level code reuse. Our tool, which we named Videos for Vulnerability Detection in Open Source, finds these orphan vulnerabilities. It's an application layer tool that builds on the world of code infrastructure, and it allows Videos to find duplicate files at a scale that has traditionally been computationally infeasible. Given a vulnerability fix in one project, our tool identifies all other projects that still contain the vulnerable code, or else that used to contain the vulnerable code, but now it's been fixed, or that used to contain the vulnerable code, the code's been changed, but we can't tell for sure if it's been fixed or not. And the benefits are to inform maintainers and users of the still vulnerable projects about the risks of the vulnerability that's in their code, and warn users that want to reuse the code about the unpatched vulnerabilities. I don't have time to cover all the results, but in one of our 4 cases, we looked at a vulnerability in a very popular graphics library that had been fixed several years earlier, and we found tens of thousands of projects that still contain a vulnerable version of that file in this libpng library. Now, about 10,000 of those were deforked projects when we didn't look at the forks, and many of them appear to be inactive, although they could still be copied and reused since they're still publicly available, and we found some cases of inactive projects that appear to be in use. We also found some popular projects, more than 25, that had more than 10,000 stars on GitHub and over 100 that had more than 1,000 stars on GitHub. And these projects aren't found like tools like Dependabot that look for dependencies, since these are cloned and committed into the projects. And we found that very few project maintainers accepted and applied the patch that we provided. So we found that copying vulnerable code is common. We found the copied code is often not fixed when the vulnerability is found and fixed in the original project where it was copied. And then sort of disappointingly, we found that many project maintainers didn't fix the vulnerability even when we provided them with a patch that would have fixed it. Thank you.
Okay, thank you very much. Again, good on timing, perfect. So let's move on now to the next one, which is a practical automated detection of malicious NPM packages.
Everyone, can you hear me?
Yes, we do.
Okay, cool.
Okay, you ready to go?
Yes. And you can see my screen.
Yes, perfect.
Okay, cool. So hi everyone, my name is Adriana and today I will be talking to you about our paper entitled Practical Automated Detection of Malicious NPM Packages, a joint project with Max Schaefer from GitHub. And for those of you who didn't have a chance to see our 20-minute presentation, this is the too long, didn't listen version. So a key term in our project is NPM, which is a JavaScript package manager that contains a registry where JavaScript packages are updated and uploaded. NPM is a very widely used package registry given the popularity of languages like JavaScript and TypeScript nowadays. In fact, around 20,000 NPM packages release updates in any given day. And as with any large system where third-party code is stored and served to users, security is a concern for NPM. However, most of the updates are mere run-of-the-mill benign package updates in any given day. Some, not so much so. Like, for instance, the package MongoDB, which tries to impersonate the popular package MongoDB by using a slightly different name, and then stealing users' information. Other packages behave like Jasmine. This package became compromised, meaning an attacker took over the code and published malicious code to also steal a user's information. So with this picture, the problem for NPM becomes how to find the malicious packages in an ocean of benign ones in a way that doesn't burden the NPM engineers with further manual analysis. So an observation we had when considering previous research as well as our own analysis of malicious packages is that they exhibit certain patterns that are repeated throughout many packages. Such patterns include making use of certain libraries or using APIs that encode information that these packages want to steal, for instance. And a potential solution when trying to automatically find patterns is a machine learning-based solution, which is exactly what we went with. A machine learning-based solution necessitates data, features, and a learning algorithm. NPM helped us with our data, giving us a data set of malicious and benign packages, which we refer to as our basic corpus. Even though this data set contained an oversampling of malicious packages, since this was the class we wanted to detect for our initial purposes, this oversampling was okay. In our features, we tried to look for certain APIs and code that would enable a package to conduct malicious behavior, a list of which you can see on the slide. But specifically, we tried to encode certain characteristics that these packages have. More importantly, we tried to see how do these characteristics change over a package's lifetime. Our intuition is that by focusing on the change, we can capture sudden behavioral differences in packages that are compromised, like Jasmine that I showed before. So the imbalanced data set that I mentioned earlier conditioned the choice of our learning algorithm. We ended up using decision trees, naive Bayes, and one-class SVM algorithms, all of which have been used in the past in scenarios with imbalanced data sets and have been shown to be successful. So using these machine learning ingredients and also further processing mechanisms, we built our complete approach, full details of which you can find both in our paper and the longer presentation. For now, I will focus on whether our approach actually works, the evaluation. We specifically wanted to check if our approach can be accurate, robust, and quick, and we evaluated our approach in these three contexts. Due to time constraints, again, the too long didn't listen version, I'll focus on the robustness evaluation for right now. For this evaluation context, we wanted to see if our approach would work in a realistic scenario and be able to reduce the manual work NPM engineers have to do. So we conducted a sliding window experiment for an entire week, where for each given day, we would train classifiers, predict the status of packages uploaded that day, and then manually triage the predictions. Then we will continue the next day, with the difference being that the triage predictions from all the days before would be added to the training set. We continued the same experiment for 5 more days. The full results of this experiment are again in our paper, but the highlights were that we found 95 new malicious packages, which were all taken down by NPM. And in addition, we found that an approach like this would help NPM engineers and wouldn't burden them with a lot of manual analysis, because the false positive rate is quite low, especially in the latter days where the rate of malicious packages to benign packages becomes more reflective of the actual rate. So to conclude, today I've spoken about the problem of finding malicious packages in NPM, which is one of detecting a highly unlikely event. Our intuition was that a machine learning-based solution that deals with imbalanced data sets would be useful in this case, and our evaluation showed that that is the case, and this would actually help NPM engineers. I look forward to reading all your questions and chatting with you, but for offline conversations, I'm also leaving my email here. Thank you so much for listening to my presentation.
Thank you, Adriana. Perfect timing again. So let's move to our next speaker, who will be talking about exploiting input sanitation to reject denial of service. And the speaker will be Efe.
Thank you.
I can see your slide and I can hear you, so you're ready to go.
All right, great. Yep, all right, everything's good. Hello, everyone. My name is Efe. I'm from the EC department at Purdue University. Today, I'm going to talk about exploiting input sanitization for regex denial of service. Well, what is regex denial of service? Regex stands for regular expression. It matches a set of strings, and this matching process is conducted by another component called regex engine. The problem comes here. Some regex engines can have superlinear time complexity, such as the orange and brown line, given certain regexes. We call these regexes vulnerable because if this computations happen on the server side, it could steal computational resources from legitimate clients, thus causing a denial of service. Previous studies have shown that 10% of regular expressions in NPM and pip are vulnerable, and that there are 350 vulnerabilities in the top 1 million websites by traffic. However, those studies assume having knowledge about the server implementation, and we wonder if we can study REDOS with a weaker threat model. So what black box approaches did we use in the study? For a client-server model, both client and server side would often have sanitization, which include regexes. Our first approach is based on the assumption that server-side sanitization repeats client-side. And here's one example from Mozilla. Because we're interested in server-side regexes, we start with the client-side, and we do that by parsing front-end HTML and JavaScript code. For the second approach, we search for the API specifications that web services publish online, and these specifications often contain regexes as well. So here are some of our findings. Oh, I'm sorry. To conduct REDOS study in a black box manner, the study is divided into 3 steps. First, we use the 2 approaches to find a list of regexes. Second, we use the off-the-shelf tool of detecting vulnerable regexes to find those regexes. Third, we probe the web services which use those vulnerable regexes, and we analyze the response times and status codes to find vulnerabilities. Now here are some more findings. For HTML forms, we have randomly sampled 1,000 websites off Tranco 1 million, and for APIs, we collected all of the documents on apis.guru, which is an online API specification directory. So starting off with this data set, we first find the proportion of web services with at least one regex in either their HTML forms or API specifications. And we find that regexes are frequently used in client-side sanitization for both interface types. We also found that in HTML forms, there was significant regex reuse. We found 5,000 regex uses in total, but only 33 of them were distinct. But what proportion of these domains use superlinear regexes? And we found that superlinear regex use varies by interface type. Out of the domains using regexes on the API side, 13% use at least one superlinear regex, and on the HTML side, only 2% use at least one superlinear regex. In total, we found 17 domains which use superlinear regexes, and now we run probing experiments on these domains to find vulnerabilities. We probe these web services by following Steiker and Pradal's methodology and sending them two types of requests. One type of request includes strings which are expected to trigger superlinear behavior of the regex. Then we'll calculate the difference between the response times to see if we produced superlinear behavior on the server side. And if we observe a difference, we conclude that there's a vulnerability. And indeed, we found 6 domains with vulnerabilities, including AWS and Microsoft. These vulnerabilities have been patched since. And if we did not observe a difference in response times, but we were able to send an initial valid request as stated in the status code, then we conclude the service either uses a safe engine or a server-side sanitization scheme differing from the client side. And we found 3 domains in the HTML and 1 API domain under this category. And if we couldn't send a valid initial request, the probing experiments were unsuccessful. We patched so we want to help software engineers mitigate against this risk, especially in the API domain. So we patch a client and server-side input sanitization library called AJV, which has millions of dependent projects, so that the users of AJV can easily switch from using an unsafe regex engine to using a safe regex engine. In our study, we found that over 99% of studied web services were safe from black box analysis. This is a very small risk, and it should inform how software engineers regard REDOS. On the other hand, Steiker and Pradal reported in their study that their gray box analysis found 12% of websites using Express to be vulnerable to REDOS. Comparing their results to ours, on the API side, we found 1.3% of web services to be vulnerable. These are our contributions. Thank you for your attention, and we're happy to answer any questions on the comment section. Thank you.
Okay, thank you, Efe. So let's move on to our last paper, which is, let's see, it's hiding critical program component via ambiguous translation.
Can you hear my voice?
Yes, I can. I can,
Okay.
yes. And I can see your screen too, so you're ready to go.
Okay, thank you. Let me start. Hello, I'm Chijung Jeong. Thank you for coming. Today, I'm gonna talk about our paper, Hiding Critical Program Components via Ambiguous Translation. Software systems often contain critical program components, or CPC, such as patented program logic. And there are a few techniques that can be leveraged to hide CPC, such as obfuscation, packing, and encryption. These techniques certainly make the analysis challenging, but it is practically feasible to obtain the CPC protected by existing techniques. In this presentation, we introduce new desirable properties ambiguity and show our proposed approach Ambiter prevents the adversary from identifying and pinpointing the correct CPC. For existing techniques for hiding CPC, first, obfuscators aim to make the original code difficult to analyze. And typically, a dynamic analysis, including first execution techniques, are highly effective in handling the obfuscation techniques. Packers or cryptors, they create a program containing compressed original program as data that uncompresses and executes the original program at runtime. And because a packer generated the program seamlessly packs and executes the original code at runtime, dynamic analysis can obtain the original program. Protectors are essentially advanced packers or cryptors equipped with evasive anti-analysis techniques. First execution techniques can handle evasive techniques by forcibly executing branches regardless of the predicate conditions. We consider 4 desirable properties of critical program components hiding techniques: evasiveness, complexity, context sensitivity, and ambiguity. And here, we introduce ambiguity as a new property. The program is not ambiguous when an adversary obtains a successfully decoded or decrypted critical program component, and the adversary can certainly say that this CPC is genuine. In other words, if the adversary cannot determine whether the CPC is correct or not, we consider the technique has ambiguity property. Our proposed approach, MBITR, aims to impose challenges in terms of not only existing three properties, but also ambiguity. Let me explain how MBITR achieves ambiguity. Ambiguity leverages the state machine. MBITR leverages the state machine, but it's different from the typical state machine. First, it makes a transition on every input. Unlike the typical state machine in MBITR, if the input does not match with any possible transitions from the current state, it makes the transition to a state which has a similar transition condition to the provided input. And second, MBITR can generate an output without requiring a state machine having a matching transition. It means that when an input is not exactly matched with the transitions input, it applies the differences between the input and the transitions input to the output transition rule. We evaluate MBITR in terms of evasiveness, complexity, and the context sensitivity. In this presentation, I will briefly explain about reverse engineering attempts using static analysis and the symbolic execution tools. The result shows MBITR effectively hides CPCs. I will briefly explain about reverse engineering MBITR using static analysis and the symbolic execution tools. First, static analysis tools can be used to analyze MBITR to identify possible output values that can be generated. A data dependency graph shows that all variables are contributing the value of the result. While this is correct, the result is too coarse-grained. It does not provide a particular order of state transitions, which is very important in revealing input for critical program components. Second, also the reversal uses symbolic execution tools to reverse engineer the genuine CPC translation logic of MBITR. However, none of the symbolic execution tools we used finished the analysis in a week because of the state explosion. So we additionally conducted two experiments to measure the time cost after we enhanced the symbolic execution tool manually. We prepare MBITR instances with different numbers of transitions and a single transition but with different input lengths. It takes about 3 hours, 2 days, and 4 weeks to finish the analysis with 4, 5, and 6 transitions, respectively. And they take more than 15 hours, 2.9, and 13 days to finish the analysis when input lengths is 6, 7, and 8, respectively. This shows that analyzing even a single transition is time-consuming. So we propose an ambiguous translator that imposes fundamental challenges to the existing analysis techniques, and more details are also in the paper. Thank you.
Okay, thank you so much. So we are done with all the paper. Thank you for the great presentations. And now we're going to move to the questions. We have a lot of questions in the chat, but we can also come up with new questions now. One way it could be maybe since vulnerability is kind of the main thread of this session, maybe we can start with Adriana. You have a question for David about vulnerability. Do you want to start with your question?
So I was just wondering how does David and co-authors define what does a vulnerability actually is? Like, how do they actually check whether this particular code is vulnerable or not?
We used the National Vulnerability Database, and so we had CVE entries that had already been reported there. We didn't specifically look for vulnerabilities. We just found existing reports of vulnerabilities. And I will note one limitation to the study is that we found cases where the vulnerable code existed in a project. We did not look to see if the project used the code in a vulnerable way. And so that did, we may report some things where a project's not actually vulnerable. We just found that the vulnerable code is in the project. But all that came from reported CVE entries.
Thank you for answering. When you look at like these CVE entries in MVD, you also have to like look at the code, right? So I'm wondering, did you look at individual functions, individual lines of code, and whether someone labeled them, oh, this is a vulnerable line or this is a vulnerable function, or did you have some automated process for that?
Yeah, we did not have an automated process, so we just manually went and looked at the NVD entry and then found the patch that fixed the vulnerability, and from that found the lines of code where the problem was. And then in the case where we sent patches to some of the vulnerable projects, then we went in and actually fixed the code. We'd fork the code, fix it, send a pull request, and see if they would accept the fix. But finding those particular vulnerable lines, that was just done manually by looking at the patch that fixed the vulnerability.
Thank you so much.
Okay, I see a lot of questions for David actually in the chat. So if anybody wants to ask David one of your questions, feel free to go ahead and mute yourself and just ask the question. There's some question from Jasmine, Zisman, and more. Aroshka, Paul wants to go ahead.
Sure, I'll go ahead.
Okay.
My question is, can we use this scanning technique on a private repository that may be incorporating open source software, or is your scanner too tightly tied to the World of Code APIs for that to work?
So yes, it can work with a private corporate repo. It will find vulnerabilities in the open source code. So if the vulnerability started in the commercial code, we don't find that, but we can certainly look at commercial code to find vulnerabilities that were created from the open source repositories that are available to us in World of Code.
Awesome, thank you.
Any other question for David?
Hi, thank you for the great talk. I just had a question. So you mentioned that most of the maintainers did not accept or implement the patch that you suggested. Do you know why? And do you think it could have to do with the fact that maybe the vulnerable code is not actually used in production or in the end product of the software?
Yes, that's a likely cause. We really got very little feedback. What happened is either they accepted our pull request or they didn't. And some of them would say thank you, and that was about it. A couple people said thank you, we'll look at it, or so we got a little bit. For the most part, we just didn't get feedback. About 10% of the projects that we submitted patches to accepted them, which means about 90% did not. We got very little feedback as to why they did not, and we didn't follow up with that or try to push it to get the answers. So I really don't have a whole lot of good information on why they did not accept the pull requests.
Thank you.
Okay, and so Jasmine, I see that you have a question for Andreas too. So maybe while we have you, would you like to ask your question for Andreas as well?
Yes, of course. I'm just gonna scroll back to it. Yes. So from my understanding of your study is that some modifications in the library code or the code that uses the vulnerability can lead to reporting false negatives. But did you see any cases where it caused false positives on the contrary?
Yes, that's actually a super question. Because an open source package has a name and a version. And you can easily produce false positives when you leave the name but obfuscate or change the version. Because if these scanners couldn't deduce from the jar file that they have at hand the exact version, some start to report just simple all CVEs that somehow match this software artifact. So a lot of they just go wild and report everything independent of the version.
Okay, that's a bit messy. Thank
Yeah.
you.
So any other question for Andreas? I see Imran, you do have a question for Andreas. Do you want to go ahead?
Yes. Vulnerability scanners only rely on names to detect and not scan the code. So why do you think that is? My assumption is that it is because they want to improve the efficiency of their tool. And if they think that they should scan the code and not just the name, and that's not the right approach, then wouldn't it increase the time and resource complexity of it, and would it make them usable then?
Okay. The problem is when checking the code, why they use names. So Eclipse Steady actually looks into the code, but it requires, as David said, a complete database that specifies this CVE belongs to this class file or this method, which is actually vulnerable to detect the vulnerable code. And this is a lot of manual effort. For open source tools, it's not manageable. They just take, or often just take, the NVD database that has a name and then do the name matching. Eclipse Steady showed that it's actually possible. So it's used at SAP, that it's actually manageable, but it requires a lot of manual effort to report, to match a CVE to a certain class file or to a certain method. And I guess the most commercial tools were, let's say, just a bit lazy because when they emerged, there was no dependency scanners available. And the easiest approach was taking the NVD, enrich it a bit, and then do the name matching. But we have tools that do so. And actually, for these, it's not too time and not too resource expensive compared to the rest of the build and JUnit test process.
All right, thank you.
Okay. In the chat, I see a number of questions for Adriana. So maybe we can start. Efe, do you want to ask your question to Adriana?
Curious about the slide where, how to say, where there was a feedback loop from each timestamp of the repositories. I was just curious what you were referring to by triaging. That was my question.
Basically, we're looking at all the results we got from the classifiers, all the positive results, meaning a package was classified as malicious, and then manually verifying whether those were malicious. So I saw your questions. It's essentially removing false positives.
Okay, and another question for you, Adriana, from Kushal. Kushal, do you want to ask your question?
Hi, just a general question. Does this approach also work with, say, Python modules or even libraries in other languages?
In theory, yes, the approach is quite adjustable. In practice, we would need to make modifications to the code because right now, especially the feature extractor is very JavaScript oriented. There would also need to be distinct features that we would need to come up with because, again, the features are very much tailored to NPM, TypeScript, JavaScript types of language. But the core of the approach, not considering how we extract the features, is also could be used for other domains and programming languages.
Okay, thanks.
Okay, and I think another question for you from Qingzheng. Can
you hear me?
Yes, we can.
Yeah. Thank you for your nice presentation. My question is about the time cost when. The question is how long does it take to analyze the package using this approach? I mean, your classifier. I wonder it depends on the target package size or not.
So in terms of the prediction doesn't take long. It takes less than seconds. The part that would take a bit longer and that it's dependent on target package size is the extraction of the features. So we generally we took a sample of 500 packages to measure how long it would take for them to extract features. And generally it took less than a second again. We did have one case of a package with around 10,000 files, which took around 10 minutes. So to summarize, the question is, yes, it depends on the package's size, but for any normal package, it shouldn't take too long.
Okay, thank you.
Okay, great. Aram, I had a question for you. If you could elaborate maybe on your research method and also on the type of delayed intervention that you were referring to.
The research methods that we used literature reviews. We basically conducted a literature review of 3 different areas. We first looked at, we did literature review, a high-level literature review of psychology literature from social and cognitive psychology that relates of individuals, and based on that we identified psychological elements that influence the behavior of individuals to achieve the goal. And then we did a literature review of developer-centered security literature, and we identified catalog of factors that influence developers in achieving their security goal. And we also did a high-level literature review of security interventions that are available, and we arranged them in a high-level review at a high level based on their presentation style. So it was purely on literature review, but we distilled information from all of them and made a case for adaptive security interventions. And for the second part about the delayed interventions, this is opposite to the interactive interventions that directly notify developers in their IDEs. And what we mean by delayed interventions are that they are built over time and they are not intrusive. They do not directly disturb the developer's coding flow, and they encourage developers to think and encourage long-term behavioral change in their secure coding behavior.
Okay, very good. Thank you. So we still have some questions in the chat, but we didn't touch on 2 papers from Efe and Qingjam. So do we have questions for them or not? Anyone of you will have question for Efe and Qingjam? Because if you don't, then Efe, maybe we can start with you, and I'm going to ask you, if there is one thing you want us to remember from your paper, what will that be? And Qingjam, you can also think about the answer to that question as well.
I think, so there have been a lot of empirical papers on evaluating the risk of redos from, a variety of different sources and a variety of different methods. I think that with this paper, this was sort of an upper bound on the general risk of regular expression denial of service, the harm it can cause to a web service. And we found that it isn't much. So we think that this informs the implications of future research on redos vulnerability scanning. That's one key finding that we found. Another one is for practitioners with API specifications, which we found to have a higher risk of redos. There are tools which generate specifications and server-side code from specifications, and we think that these might unintendedly expose superlinear regexes that are used on the server side to clients, and that's something to keep in mind while using these tools. But yeah, those are the 2 findings that we got out of this paper.
Okay, very good. Any follow-up for Efe? No? Well, in that case, I will ask the same question to you, Qingjam. What is the one thing you want us to remember from your paper?
I think one thing would be the new desirable property that we defined additionally, which is ambiguity that I mentioned before. And the next step, the next thing would be the how we try to achieve this ambiguity using our embedder. Actually, we focused on the differences between our approach and the typical state machine. So we try to make every transition on every input, and the second thing would be we try to output dynamically, and a third thing would be our evaluations are all focused on we try to show this effectiveness. So I think the readers, if the readers can focus on this additional desirable properties ambiguity and how we achieve this, it would be more helpful.
Okay, very good. We're getting toward the end of the hours here, but still we might have a time for one or two more questions. So is there like one of you would like to ask one more question to one of our authors, presenters?
Question for Jijung, actually. I was just wondering, I saw a bit of the presentation also in the paper that you have all of these, as you mentioned, you want to reach ambiguity, so you want you have all of these different variations of the program where one of them could be the actual critical component. So I was wondering, like, when those programs are executed, how do you decide which one to execute? Is the goal to like not execute the correct one?
Can you hear me? Can you?
Yes, we can hear you.
Yeah. I'm sorry, but there's some